Welcome, geologists, and we're here today to talk about the Ordovician period. This is the second of the 7 that make up the Paleozoic, and it's referred to as the age of the great biodiversity event. So remember that the Cambrian was the age of the trilobites. We have some rapid diversification that happens after we had lost quite a bit of life at the end of the Cambrian period. So let's take a look at the events that happened in the Ordovician and talk about the animals that evolved during this remarkable time period. The Ordovician is one of 3 periods that makes up the early Paleozoic. The early Paleozoic is made up of Cambrian, Ordovician, and Silurian. So this is the middle of the 3. And the Ordovician is subdivided into early, middle, and late. Each one has its own important aspects of things that occur during that time period. We use a specific fossil in most cases to age date Ordovician rocks because it's so heavily found in this age rocks around the world, called graptolites. We'll be looking at what graptolites represent later in the Ordovician lecture. We need to discuss the Sauk Sea before we get started on paleogeographic information for the Ordovician. In the early Ordovician, the Sauk Sea completely regressed off of the North American craton. So we know that the Canadian Shield and the transcontinental arch islands were exposed during the Cambrian period, so they were highly eroded. But now those areas that have been covered by the Sauk Sea are re-exposed to the same elements of weathering and erosion. So a lot of our freshly laid down sediments get erased from the Sauk sequence before we can lay down new sediments in the Tippecanoe, which is one of the reasons that the Sauk Sea has such a thick black area right here, which represents a major unconformity. In the middle Ordovician, the Tippecanoe will start its transgressive phase, and we'll get to that in just a minute. So let's talk about the significance of this unconformable contact, because there's very few places that we have a very good record of this time frame, because so much of the rocks got erased because they were in low-lying areas. We had no mountain building on the craton yet. That's fixing to change in the Ordovician. So everything's still flat. It's still low relief. We probably even have basins that have formed because of the extra weight on the ocean floor and on the craton from all the extra sediments that were laid down during the Sauk sequence. During the Middle Ordovician, the Tippecanoe begins its transgressive phase and will continue transgressing all the way through the Silurian and come off during the early Devonian. What's important about this is throughout the Ordovician, we see a very clear pattern of the sea coming in from all sides of the craton and leaving behind a really solid sandstone unit that's clean, quartz mature sandstones. You should remember from the Cambrian period that means that they're well-rounded, sorted by size, and that they are pretty much solely made up of quartz. So that's important to this particular period because there is a famous rock layer that's used in manufacturing of glass and other types of silica-related needs that is called the St. Peter sandstone. And I'll be showing you an outcrop of it in just a second. This is a piece of the St. Peter sandstone, and it represents the beach deposits that were coming in as the transgressive sea worked its way in during the Ordovician all the way through the Silurian. This is the St. Peter sandstone. This is actually one of the mines that exists for this area or for this particular formation. And as you can note that it's very clean. In other words, it's very similar in size. So the St. Peter sandstone shouldn't always be associated with the Ordovician transgressive Tippecanoe Sea. An important theme to understand when looking at paleogeographic maps are that the plates are moving constantly. This is our first chance since the Phanerozoic began to really see the impact of a plate and how it affects the continents or the craton. We're going to see this particular landmass come in and smush up against us right here. So that's going to be important because this brown area represents highlands. And when this occurs, there's going to put mountains there. So we'll have our first orogeny during the Ordovician event. Obviously, mountain building is going to change climate conditions. It's going to change where animals can live. It's going to change topography. And also, it will yield sediments because those mountains that get erected must also be eroded down to ground zero again. Those sediments get deposited as rock layers onto the continent. So with that in mind, as plates move around, things are constantly changing. Our ocean currents are changing. Our temperatures and climate, our location of the plates are changing. Those dynamics are never static for very long. That theme, it surfaces beginning in the Ordovician when we see our first mountain building event. So we're going to get this place is called Avalonia, which is right here. And Avalonia is going to be pushed into Laurentia because of a divergent plate boundary over here. So in other words, we got a mid-oceanic ridge that's pushing the ocean crust this direction, and it's going to squash into Laurentia. When it does, it's going to cut out this ocean and make it smaller. We learned about this ocean back in Cambrian period. And so this is important to note that as we lose this ocean basin, any kind of ocean sediments that are in this area right here are going to get squashed. And they're going to get squashed up in terms of folded rocks along this mountain range right here. So during the Middle Ordovician, the subduction of this microplate beneath Laurentia produced the first orogenic vent that we're going to have. And that's this island arc that you see right here, the Avalonia island arc, and it's going to squash up and it's going to smash up against Laurentia, and anything in its way will be folded and put up on those mountains. So the tectonic orogeny is the name of this particular mountain building event. And the Appalachian Mobile Belt is actually divided into two different sections of depositional environments as a consequence of the way that it's made. The first area of deposition are the extensive shallow water platforms that created lots of carbonate rocks like limestone. So that would have been the continental shelf that extended out towards the sea. That's the stuff that's fixing to get squashed. The deep water deposits are made up of black shales, graded beds, coarse sandstones, greywackies, and even volcanic material that is associated with island arcs for our first mountain building event. These are some of those shales that are going to get made as the tectonic orogeny starts to work its way and build up the Appalachian Mobile Belt for the first time. This will not be the last, however, during the Paleozoic. There are multiple episodes of mountain building in the Paleozoic, and then it pretty much stops. And we'll be talking more about that later in this semester. What is the proof that we actually had the tectonic orogeny? First and foremost, we have ancient lava flows that can be documented from this particular event. Subsequently, we have volcanic ash layers, pyroclastic material. We also have the magma plutonic structures like batholiths that are associated with this particular event all the way from the south up through Newfoundland. So we've got lots of evidence that this occurred. But some of the most important evidence comes with what's called a clastic wedge. This is the detrital sediments that get deposited as these mountains begin to erode, and it makes what's sediments that are wedged up against a mountain range, and those clastic wedges are distinctive because of the erosion of the volcanic seamount, or in this case the tectonic mountains that got uplifted in the Appalachian Mobile Belt. The rock layer that's famous for that in North America is called the Queenston Delta, and it's used for lots of economic purposes, including materials used for construction. In the late Ordovician, the island arc collided with Laurasia fully, causing intense metamorphism of all of those sedimentary rocks and even the lava flows that had already squished up further north, and then we close it off going further south. So this terrain was permanently accreted onto the North American continent, adding landmass and states to the United States of America. So this is another one of those add-ons that we get in terms of new continental material because of an island arc. It's a theme that happens. So here is the island arc coming in. This is the subduction zone, and you can see as it's coming in, do you see all this sediment right here that's getting squashed up? Well, that's the seabed layers. Well, those get shoved up onto the continents, and they're embedded in these mountains, so you get highly folded and metamorphic type of situations in these types of mountains where you get that type of compression. In the Tippecanoe rocks, there are a couple of things that you should note. The basal sandstones were followed by a widespread carbonate deposition, but the sandstones are very special to the Ordovician period. That would be the St. Peter sandstone. The limestones are made up of calcium carbonate, CaCO3, by organisms like corals and brachiopods, stromatoporids, and even bryozoans. In some cases, in Ordovician rocks, bryozoans are so heavily embedded in fossiliferous rock that they are almost the exclusive organism that you see. So some of the limestone made in the Ordovician got converted into dolostone because magnesium replaced the calcium that was in the calcitic material. So we have quite a bit of dolomite or dolostone from the Ordovician in addition to limestone. So you might ask, what does carbonate deposition look like? Right, what you see right here, this is the Great Barrier Reef. These are little patch reefs within the Great Barrier Reef. And carbonate deposition looks like this. So this is the image that I want you to have of the Tippecanoe as it transgressed over the North American craton, and even the middle of the continent was completely covered. So when you did your sloth slab, you should have been able to draw and notice that the transcontinental arch and the Canadian Shield, at least most of the Canadian Shield, was actually covered by the Tippecanoe. Certainly all the islands were, and there was just a handful of places exposed, which would have been the Taconic Highlands. This is an example of some of the carbonate rock that's exposed in the Ordovician, representing the transgressive Tippecanoe Sea. A couple of things I might point out. Notice there's some ripple marks in here. That's indicative of, let's go back one. Do you see the ripple marks not just on the water, but that's also in the sand grains that are down there. And this is carbonate-based sand, so you're going to end up creating a limestone type rock over a long period of time because there's no detrital material there. These are stromatolites. So you look at these and you're like, okay, I buy off on that. As stromatolites are going to be in shallow marine areas where they're going to follow the coastline where the beach line was all the way into wherever the beach stops. So once we get full coverage of the continents, stromatolites will be in areas that have the right depositional environment for them to survive, which would be very shallow marine waters. Considering the Tippecanoe is the deepest of all of our sloth sequences, there wouldn't have been too many places except along the shorelines where you would find stromatolites. On the eastern margin of the North American craton, carbonate rocks grade into shales. Why is this important? Because the shale layers represent erosion of the Taconic Highlands, this kind of material right here. So when Avalonia collided with Laurasia, it created a mountain range. And this mountain range, which is the fate of every mountain range, got elevated and erected and had to be eroded down back to ground zero, which is sea level. So those sediments go somewhere and they make new rock layers, and that's the detrital material that's making these shale layers that are Ordovician in age. Late Ordovician and certainly Silurian aged rocks are famous for large-scale carbonate production of rock material. So by the late Ordovician, we were cranking out coral reefs and we were starting to produce lots of carbonate rock like limestone. That makes the perfect habitat, since we got a shallow marine environment on even the middle of the continent, for big, large-scale barrier reefs to start forming. And they'll be instrumental, especially during the Silurian period and again during the Devonian period. So let's look at some of the Ordovician life and fauna. I mentioned earlier that bryozoans were one of the very important organisms of the Ordovician. If you look at your textbook in the table that talks about the invertebrate paleontology in terms of when did things first appear, you will notice bryozoans, or phylum Bryozoa, does not start until the Ordovician. So they made their first appearance during the Ordovician. By the middle Ordovician, you have rocks that look like this that are so fossiliferous, full of bryozoan deposits, that it's almost hard to differentiate any other types of fossils, or sometimes even the rock type, because it's so full of bryozoan fossils. Bryozoans are referred to as moss animals. They are marine. Certainly in the case of Ordovician, where that's all the animals we had were in the ocean at that time. Now, it's important to note that they like tropical to temperate climates, and of course we had basically all tropical in North America during the time of the Ordovician of the Tippecanoe. They must require some type of a hard substrate or rock to build their infrastructure on, and then they're going to need clear, agitated water that allows them to pick out their suspended food matter in order to eat. So that dictates where they're going to live. They're going to live pretty much in close to the shoreline areas where the water is fairly vigorous and moving quickly, and they're going to anchor themselves onto sediment. It's more typical that you'll see something called a lacy fenestrate bryozoan, which I'll show you a picture of in a second. And then there's some special types which are branching ones, and you can see both, but depending on the time of the Paleozoic dictates what type of bryozoans you're going to see. If you get your book out and you look at the table that introduces the invertebrates and when they first appeared, you're going to notice that bryozoans made their debut in the Ordovician. This is a lacy fenestrate bryozoan. It's a good example of an encrusting moss animal on top of a rock. So if you got these growing in large concentrations, and considering they're all colonial, you can imagine that they would help anchor in sediments at the bottom of the ocean. And it's just, they're good for preservation in that sense. Brachiopods are known as lamp shells. Why are they called lamp shells? They look like oil lamps, so they're kind of unique. They don't all look the same. There's a lot of different varieties, but we learned a little bit about them in the Cambrian, because if you recall, they made their debut in the Cambrian, but they diversify rapidly during the Ordovician. The name brachiopod, brachio means arm foot, because the arm is the brachio and the pod is the foot. And what brachiopods do is attach themselves to a rock, and they'll do it by using a mechanism like this. So you get this feature right here called a pedicle, and it allows them to anchor into the sediment so they can suspension feed. They are filter feeders, and they're very fascinating animals that they figured out how to work and do and fill a niche that the mollusks did not. At first glance, you may look at these and go, hey, they look like a bivalve. Well, there's a few fundamental differences. First of all, you always look at a brachiopod flat on, and you can divide their shells based on the top of them directly equally in half. Where a bivalve, it's just the opposite. The pieces match on each side. So let's look at that in a diagram. Here is a brachiopod right here, and here is a bivalve. Notice that these are mirror images of each other. These would not be. But they match. If you take your hinge right down the middle, they're going to match on the left and right side, where the tops and the bottoms would match on a clam or a bivalve. So superficially, they may look like clams, but they are anatomically very different. While they are both suspension feeders and possess shells that have two valves, they have a different morphology and a little bit of their anatomy. Let's take a look at that. First of all, brachiopods use muscles to open and close their shells. Not the case for a bivalve. Bivalves actually use a muscle to close their shell and a ligament to open them again. So they have a little bit different format. The valves are different size for brachiopods, while the valves are mirror images of each other in a bivalve. So remember, you look at the plane of symmetry for a brachiopod, it runs perpendicular to the valve, or to the hinge right here, and this would be the marker that you'd look at. So this half matches that half. That's how you know you got a brachiopod and not a bivalve. There are two distinctive groups of brachiopods, and both are found in the Ordovician. Inarticulate and articulate brachiopods. Probably the most famous inarticulate is the lingula. Lingula is still alive today, and this is actually one that your book talks about as being kind of a complex problem for evolution because it really hasn't changed that much since it first appeared in the early Paleozoic. These are spoon-shaped fossils, and they were held together by muscles and soft parts. So they don't have an interlocking tooth and socket mechanism right here that allows them to have a hinge like this one does right here. So this is an articulated brachiopod. You can see its hinge, and it would have opened and closed along that hinge line right there. So in both cases, you can draw a line right down their hinge process, or right where they would be, and see that the shell itself is the same on either side. Do it on the lingula right here, and you can do it on the spirifer, which is a special type of brachiopod in the bottom. It kind of looks like it has wings. Another type of Ordovician life is echinoderms. We start seeing complex echinoderms during the Ordovician. Kind of an exciting thing. Echinodermata means, quote-unquote, echino, spiny, and then skin for dermata. So if you've ever been to a dermatologist, derma means skin. All echinoderms are 100% exclusively marine. So if you find one in a rock, you've automatically narrowed the scope that they are in a marine-based rock. In other words, that's where they died. Probably where they lived as well. They have calcite skeletons, and all of them have radial symmetry, which gives them a benefit ecologically. What do I mean by that? Their fivefold symmetry that they have allows them to suspend themselves, looking for potential food and sensing for predators that they may have. At first glance, echinoderms don't look that complex, but they have an entire water vascular system, a mouth, a stomach, and even an intestines. So you have to realize that these are complex animals, not too different from us, they just don't have backbones. And so when you look at one and you find the next sand dollar you find on the beach, I want you to take a moment of respect and realize that that echinoderm was a very complex living organism. So what are some things that are echinoderms? Starfish, brittle stars, sea urchins, very common one. My least favorite would be sea cucumbers, sand dollars, crinoids, blastoids. These are all examples of different types of echinoderms. So which ones arrived during the Ordovician? So this is a blastoid, which is a cousin of your crinoid right here, and this would be a sea urchin. A couple of things to note. This is the actual morphological shape. So is this. So they're three-dimensional. On the crinoid, look at this right here. That are the little columns make up their stem, and the stem also allows them to grow and have a flower at the top which spreads out, and these are their feeding mechanisms right here. An interesting thing about crinoids is they have a little foot that we'll learn about later in the semester in the Mississippian period, when these are index fossils for. And we'll talk about how they moved around because they're kind of fascinating. So this is a crinoid fossil, and you can see its calyx right here, its brachioles, and then here is its stem right here with all of its little pieces. So crinoid stems are very important in the fossil record. These are chunks of crinoids in a rock layer, and there's some rock layers that are so heavily embedded with crinoid stems they almost look clastic. These are crinoid feet, and you can see the little feet, and they're going to be able to allow the crinoids to stick onto the ground. Here is your crinoid stem. Here is your actual crinoid flower. Again, this is the most common portion of the animal that you would find. When you look at ancient crinoids, here's full crinoid flowers. Here is a modern-day sea lily. Do you see the resemblance? The crinoids from the early Paleozoic have gone extinct, but their residual leftovers, we still have a lot of echinoderms left in the rock record, and some related to crinoids, which would be your sea lilies, your sea fans, brittle stars, things of that nature. So we'll be looking at some of those later in this semester. It is very noteworthy to mention that the first corals appear in the rock record during the Ordovician. There are two types of corals. There are tabulate corals and rugosa corals. So we'll come back in a few minutes and we will talk about these corals, and we'll see you back for the second half of Ordovician. Bye.